Well, good evening again, and welcome back to our at-home planetarium show that we've been calling Your Sky and Solar System. And hopefully you've joined us on Facebook Live just a little earlier to see my introduction tonight from Stone Mountain. If you didn't, again, my name is Scott Harris. I'm the staff planetary geologist for Fernbank Science Center and the Jim Cherry Memorial Planetarium. And over the next few weeks, we will be exploring more of the geology of our state as we continue through the summer. And if all goes well, next week we'll have something truly epic for you that I really look forward to being able to share. But we're going to start our look at the sky tonight by looking off to the west. We'll go ahead and get that started now with our Stellarium program. And as we look out to the western sky this evening, right at sunset, this is about 9 o'clock, there's not a whole lot to see there, right? Except the glow of the sun. But if you look carefully to the northwest, you will see one of the brighter stars in the nighttime sky. This is Capella, the brightest star in Auriga, the charioteer. Now, over here to the west, slightly to the southwest, we see Procyon. That is the brightest star in the Little Dog, or Canis Minor. Right in between, just barely above the treetops, maybe you'll see a very faint but crisp whitish blue light, and this actually is the planet Mercury. So this is one of those times of year where if you do have an unobstructed view of the horizon, you may be able to see the closest planet to the sun there in the western sky. Now, I'm going to let time advance here. We're actually going to skip ahead about an hour in time so that it's nice and dark outside. We'll do that now. There we go. And we'll look up a little higher in the sky. Now we have about 10 o'clock at night. And if we look straight up toward the top of the sky and a little bit to the north, we can see a pattern that everyone is familiar with. These 7 stars in the shape of a pan with a handle attached that, of course, we call the Big Dipper. Sometimes people are surprised to know that the Big Dipper is not a constellation. It is actually a pattern of stars that we call an asterism, which basically is a fancy term for a pattern made of stars. But like some asterisms, the Big Dipper is part of a constellation. It's actually the back and the tail of Ursa Major, or the Big Bear. If you look carefully and follow the curve of the tail down the back, you'll find a leg that ends in 2 toes. If you look behind that, you'll see another 2 toes. Out ahead, you'll see 2 toes, another 2 toes. 4 legs all together, making it look like the bear is running off to the horizon. My astronomer friends are fond of pointing that out, that if you take the arc of the tail, you can follow around the sky. We'll see if we can do this here without too much trouble. There we go. We'll follow around that arc, arcing, as they say, over to another bright star that is called Arcturus. Arcturus is the brightest star in the constellation of Boötes, the herdsman, one of the more interesting constellations when it comes to pronunciations. Now, at this point, I always say, if you are, if you really can't follow me saying that there's a bear here and that sort of thing, this is where we can help you out with our program by taking a look first at the patterns here in the sky. We see now that back and the tail of the bear. And we'll move around here so we could see Boötes a little better. If you can find Arcturus, you'll see, well, I don't know if I see a herdsman or not. But what I will tell you that you can look for to find Boötes requires us to actually take those patterns away a second. And you'll see these stars, 4 stars in the shape of a diamond. And then it looks like Arcturus is here off the end of that diamond. So rather than a herdsman, I often think of this as a kite with a tail attached, with Arcturus, the decoration or ribbon at the end of the tail. Now, if you want to imagine what the ancient Greek and Roman astronomers had in mind when they looked up at the sky, we can try to help you out with the artwork. Now we see, well, maybe a herdsman. We see Virgo the maiden here with this trapezoid in the middle representing her body. And beneath that, near to the horizon, looking off to the southwest, about between 10 and 11 o'clock tonight, we can find another trapezoid. This is Corvus the crow pecking at the back of Hydra, the sea serpent. Now I'm going to move around to the southeast here, and we're going to see something very familiar. We're going to have our moon out there. Just to the south of the moon, we'll see Scorpius rising with the red bright star Antares. And just a little bit to the north of that, we will find our moon tonight. We can take a look at it here up close so that we can get a better view of it. And as we see, our moon is full. So it will be rising, looking huge with that famous optical illusion above the horizon tonight. As you look at it, you can imagine the ancient history of the moon with its old feldspar crust, the ancient lunar surface, pockmarked by these huge impact basins from collisions that occurred between about 3.8 and 4 billion years ago, and then later, in hundreds of millions of years later, up until about 1 billion years ago, these basins filled with ancient lava flows. All right, so I'll back off the moon there. And I'm going to keep looking to the southeast, but we're going to take our constellation and artwork away, and we're going to advance time again now a little more quickly as we go from 11 o'clock, 12 o'clock. We'll watch the sky move by, and we see trailing the moon a couple of other bright objects coming up. So by about 3 o'clock in the morning, if we look from our moon down to the horizon, we will see 3 bright objects here: the king of the planets Jupiter, followed by the ring world Saturn, and red Mars rising there to the east-southeast. All right. Now, I'm going to go ahead and start our feature presentation of Birth of Planet Earth, and hope you enjoy. If you do have any questions, feel free to email me at scott.harris@fernbank.edu. I hope you enjoyed the program this evening, and hope to see you again next week, as I said, for a truly epic, geologically centered show. All right, give me just a moment as we move back now to our feature show, and have a wonderful weekend.
Gazing down from space, we marvel at Earth's bountiful oceans and continents, its life-giving atmosphere. We ask, how did our planet begin? How did it come to support life? And life to support Earth? To find out, we peer back in time, some 5 billion years ago. The story of Earth starts within a giant spiral galaxy, the Milky Way. At 100,000 light-years across, the galaxy is a cauldron of swirling dust clouds and glowing gas. This simulated view shows a 50 million year span, a cosmological blink of an eye. In that time, millions of giant stars live and die in staggering explosions called supernovae, shown here as flashes of light. They seed the cosmos with the stuff of planets, carbon, silicon, iron, and more. In one distant corner of the galaxy, a supernova shockwave slams into a cloud, already rich with these elements. The impact collapses the cloud, sending stardust streaming into its core. The cloud is about as cold as the universe gets, but the tighter it's packed, the more it heats up. A storm erupts at its center, a vast raging hurricane of dust, gas, and ice crystals. In its eye, temperatures soar. A star ignites. Our sun is born. It is being fed by a slowly spinning disk, the cradle of our solar system. Within the disk, planets take shape in a long and violent process. It starts with dust, gathering into sand-like grains. They form pebble-sized objects within clouds of loose gravel. Over millions of years, gravity draws them together to form rocks, ice balls, and boulders. These objects coalesce into miniature planets, or planetesimals. One such body, the primordial Earth, is growing steadily, but its fate hangs in the balance. What began as a gentle mingling of matter is about to get ugly. A computer model recreates the first 100 million years of our solar system by simulating the interaction of dust, gas, ice, and boulders. Each flash marks a collision. Each ring tracks the orbit of a would-be planet. While some break apart in collisions, others grow large. Out on the periphery, far from the sun, a giant emerges. Jupiter. Within a million years of its birth, Jupiter succumbs to the gravitational pull of the inner solar system. It begins to spiral toward the sun. Scientists call Jupiter's big move the Grand Tack, named for the turn a sailboat takes into the wind. Along the way, Jupiter plows through clouds of cosmic debris. What it does not swallow, it flings out of the solar system. The closer Jupiter draws toward the Sun, the more cosmic clutter it clears away. Jupiter moves all the way into the orbit of present-day Mars. Ultimately, another giant planet, Saturn, grows large enough to pull it back out. Jupiter's grand tack has reduced the mass of the inner solar system. Now, any planets that form there will be relatively small. That includes Earth. Earth is still just an embryo of the planet it would one day become. Now that Jupiter has moved back out, Earth and up to 30 hungry competitors are free to scour the inner solar system for scraps. They blend together. They blow apart. Which ones will survive depends on the luck of the cosmic draw. In one heady 50 million year run, the roller derby of planets goes wild. As the remaining planets tug on one another, their orbits destabilize. A new round of collisions leaves just a handful of would-be worlds. The time is about 4.5 billion years ago. Earth may harbor volcanoes on its surface and a thin, toxic atmosphere. Our planet has so far withstood the onslaught of planet formation. It now awaits the test of its life. Another planet, about half its size, is closing in. This is Theia, a world that might have been. Instead, its journey ends here, as it bears down on Earth. Imagine the view from Earth, as the ultimate threat looms large on the horizon. Theia rocks Earth to the core. According to one major theory, Theia shears away a third of the planet. But instead of destroying our world, Thea becomes part of it. A computer simulation captures the first 24 hours. Debris unleashed by the collision envelops the Earth in a dense atmosphere of vaporized rock. The cloud coalesces into a ring, a belt of molten rubble. Much of the orbiting debris rains back to the surface. But within a century, what's left gathers into a single, wondrous body. Earth's companion, the Moon. After the impact, our planet is left spinning rapidly on a slightly tilted axis. The Moon orbits much closer to Earth than it does today. From its surface, our world would have filled the sky. As the Moon gradually slips into a more distant orbit, it exerts a drag on Earth. It slows our planet's spin and steadies its tilt. The Moon serves as a reminder of the cataclysm that almost spelled the end of our planet. But from here on, it would be a welcome constant, a source of stability and ultimately, beauty. For the next tens of millions of years, the steady barrage of debris from space does not let up. But asteroids don't just rain hardship. They also carry massive amounts of water. The pummeling may also have released water, bound to minerals deep beneath the surface. Half a billion years after the birth of the Moon, Earth has cooled dramatically. It's now a world of water. Its seas span every horizon, broken only by volcanic islands. It's also rich with chemicals, with all the carbon, nitrogen, oxygen, iron, and more that came with the dawn of the solar system. The planet has everything it needs to accomplish its ultimate feat, producing life. But there's a problem. Its water is disappearing. The young sun is prone to powerful flares that strike the upper atmosphere. When a solar particle hits a water molecule, H2O, it can blast it apart. Lightweight hydrogen wafts into space, while heavier oxygen sinks to the surface and binds with rocks. Through this process, solar radiation would ultimately strip our neighbors Mars and Venus of water. To avoid that fate, Earth is in a race to give life a foothold before its water runs out. Incredibly, life itself may hold the answer. A process that keeps living organisms alive might also keep the world wet. On the fringe of volcanic springs, they're cooking away. Proteins and nucleic acids, the chemistry of life. We don't know exactly how life sprang from cauldrons like these. What we know is that life did emerge, and that it spread, thanks to a key breakthrough, the ability to turn sunlight into energy. Photosynthesis, the process that fuels plant life, made its first appearance in simple bacteria over 3 billion years ago. Using one of the world's most powerful supercomputers, scientists have sought to model its chemical secrets. Step 1 is to capture sunlight. Passing through a transparent membrane to the center of the bacteria, we encounter a cluster of spherical pods. Each one is equipped with special sensors designed to harvest solar energy. When a photon hits, it excites rings of chlorophyll molecules. This energy is transferred across a family of proteins, the machines of life. Down the line, electrons and protons carry the energy through a chain of chemical reactions. The energy driving these reactions came from the sun. The cell must now convert it into action. It's the energy stored in protons that gets things moving. Streaming into watery spaces within the cell, they flow toward a towering molecular structure. As they enter, their electrical charges turn a protein like a crank. This turning motion initiates a chemical reaction, one that is essential to all life on Earth. Two molecules join to form a third, called ATP, shown in blue. It is the universal energy currency in every cell that has ever lived. Like a biological battery, ATP stores energy captured from the sun, repackaged in a stable form that the cell can now use. To break down food, to power locomotion, to fuel reproduction, to live. ATP made it possible for microorganisms to flourish and evolve. As bacteria gave rise to plants, a more advanced form of photosynthesis released a byproduct, oxygen. Over time, this new supply of oxygen would change the chemical composition of the atmosphere and stem the loss of water. Earth avoided the fate that befell its neighbors as life spread to its every nook and cranny. Earth today, endowed with ocean atmosphere, and land, with light and warmth, with life that's bountiful and in balance. But think of all it took to achieve that. The aftershocks of a supernova, the violence of Jupiter, a chance collision, and the gift of a moon, of water and life. The more we're able to reconstruct our past, the more singular it seems. That is, until we realize how very many other solar systems are out there. We ask, is Earth just one of countless life-bearing worlds in a galaxy bursting with life? Or is it a wondrous twist of fate? A remarkable convergence of chemistry, energy, and chance? Our planet became a paradise. But is it the only one?
All right, I am actually back sort of in the dark now, which is the way we will end this evening. Thank you again for being with us. I hope you have a wonderful weekend, and hopefully you can join us next week for a look at our planet Earth in a very unique way. So again, thank you so much for being with us.